Section 3.2, the dependence of internal energy on volume and temperature. So du is the exact differential of the internal energy. This equals delta U over delta T times dt plus delta U over delta V times dV. So this is simply a two-step process. In the first step, you have constant volume. You change temperature. U changes. In the second step, you hold temperature constant. You change volume. And then this part tells you how the internal energy changes. Therefore, the sum of these two is the sum of the internal energy changes in the first step isochloric and the second step isothermal. And overall, this tells you how this internal energy changes when T and V change. What about the pressure dependence? Does internal energy depend on pressure? Yes. Yes, the internal energy does depend on pressure for real gases, for liquids, for solids. However, that dependence is included implicitly in here. Okay, so if pressure change, that will cause the temperature and volume change. So it's already here. Pressure is a dependent variable. Temperature and volume are independent variable in this case. All right, and then you may ask, can we rewrite this expression to show that the internal energy depends on temperature and pressure? Yes. Just replace this V, and this V with pressure. And then you get a new equation. And that equation is also correct. But that equation is not very useful because this one, if you look at this one, delta U over delta T under constant volume condition is simply this CV, the isochloric it's isochloric heat capacity. So this is convenient. For an ideal gas, delta U over delta V is 0, so this part is 0 for an ideal gas. Again, for an ideal gas, you only depend on temperature. Over here, temperature is held constant, therefore this part is 0. And then, for an ideal gas, this du is simply CV dt. For a real gas, delta U over delta V is non-zero. So later, we will derive the expression of this. This U should also depend on volume. The reason is, when the volume changes, the intermolecular distance will change. When the volume increases, the distance between gas molecules increases. When the volume decreases, the intermolecular distance also decreases. And why is that important? Well, when the molecules are farther away from each other, the attraction and repulsion between those molecules both decrease. When the molecules are closer to each other, the attraction and repulsion increase. So delta U over delta V is called the internal pressure. So one reason it's called internal pressure is because the unit of delta U over delta V is Pascal, the same unit for pressure. And why it's internal pressure? Again, U is called internal energy. This is how internal energy depends on volume. That's why it's called internal pressure. So we will be able to prove this later after chapter 6. For now, let's just accept this equation. This equation is useful because internal energy is rather abstract. It's hard to measure the potential energy and kinetic energy for a real gas or liquids or solids. However, it's a lot easier to just measure the pressure and temperature. For an ideal gas, we can prove that this is 0 because for an ideal gas, delta P over delta T is simply nR over V. And then this part is simply 0. The internal pressure of an ideal gas is 0. For a van der Waals gas, we have a different equation for pressure. We need to take the finite size of molecules into account. We need to have this V subtract this MB to get the available space. And over here, this is the attraction, The higher the attraction, the lower the pressure. Therefore, we have a negative sign here. The parameters A and B are always positive. Now we can evaluate delta U over delta V, the internal pressure. We just need to look at delta P over delta T. It's simply NR over V minus NB. This part does not depend on temperature. Alright, and then we simplify this part. Minus P, we plug in the expression of P over here in here. And you'll realize that this part will cancel with this part. The result is AN squared over V squared. So the internal pressure of a van der Waals gas is always positive. It's AN squared over V squared. Actually, it indicates the limitation of the van der Waals equation of state. Supposedly, U depends on V because the attraction and repulsion depends on the intermolecular distance. However, in this expression, you see only attraction term. There's no repulsion term. So that's actually the limitation of the rather simple van der Waals equation of state. Now, in summary, du equals delta U over delta T times dt plus delta U over delta V times dV. This equation holds true for all substances, including gases, liquids, and solids. If the process is isochoric, then dV is 0. So du is simply cV dt. If the process is isothermal, then dt is 0. du only depends on dV over here, and then this part can be expanded into T times delta P over delta T under constant volume condition, and then minus P. Over here, if you recall the definition of beta and kappa, so this part is simply beta divided by kappa.